Hi all, Dr. Clark here again, and for this segment we're going to talk about wildlife and the forest. In fact, this is kind of going to be a two-part lecture series, at least two-part lecture series. The first part, I'm not actually going to talk about wildlife, I'm going to talk about fisheries. Now, most of people know that if you uh, change the habitat and you're affecting insects, aquatic environments, that if you affect an aquatic environment, you're probably going to affect the terrestrial environment. Okay? So if you affect aquatic insects, you're going to affect fish. Fish then are consumed by terrestrial vertebrates, and you'll affect them also. You can also affect the nutrient loads, etc. Okay, so the first part, we're going to start at those organisms, lower ordered organisms, typically considered, and build our way up to kind of the fuzzy, feathery, furry individuals that most people think of when they think of wildlife. Okay, so before I get started, though, I thought this comic strip was a very appropriate comic strip for the topic at hand. And so you can see there a logger and another individual, another logger next to him holding a little sapling tree. And it says, well, that's that. Do you have the replacement ready? And, they're standing next to, a 400, 500 old tree that they cut down. And they're going to replace it with a 1-year-old tree. So yeah, I just want to make it clear that I'm not against logging by any means, but you have to realize, what are you doing to the landscape when you remove something from the landscape that might be 400, 500 years old, and you're replacing it with an organism that's 1 year old. You have to realize that it's not going to be the same landscape. You've altered the landscape. So that's where wildlife and the forest come in. We're often interested in wildlife. We're often interested in keeping wild animals and seeing, deer and bear and wolves and having fish to fish and organisms to hunt. We also need to know, though, as a forest manager, what happens if you alter the environment? What happens if you alter the forest? What are you going to do to the wildlife? Okay, so that's the first part. The second part of the lecture is we're going to talk about the role that wildlife plays in altering the forest habitat. Okay, and we'll come back and look at that in a second. Okay, so first we need to talk a little bit about the life zones, the three life zones. So the three life zones are freshwater, marine, and terrestrial. Okay, and they all interplay. Okay, they all determine, you know, the quality of each other. So we have freshwater systems that are going to feed marine systems that feed terrestrial systems, freshwater feeding terrestrial, terrestrial cleaning, or cleansing the freshwater in the marine systems. They're all interconnected, okay, and they all play a very important role. All of them play an important role in forest management, even though there are very few forests that are directly associated with marine environments. The marine system still plays a essential role in determining forest management. Okay. Terrestrial biomes, there are quite a few terrestrial biomes. Desert, tundra, grassland, temperate forest, coniferous forest. Those are a few that are very important to North America. Of them, probably the most important when it comes to forest management and forested habitat are the temperate forest and the coniferous forest. Now, that being said, I'm not saying that desert environments don't have forests. They do. Or tundra doesn't have forests associated with them. They do. Grasslands have some forest. Okay? But by and large, the temperate and coniferous forests are where you're going to have large amounts of management. Okay, so that's where we're going to kind of concentrate our kind of examples and our efforts is in these temperate and coniferous forest biomes. Okay, before we get there though, and we start looking at specific examples of alterations and the role that wildlife would play or the role that forest plays on wildlife, we need to talk about some systems, and we need to talk about some systems from a water standpoint, a freshwater system. Okay, so the freshwater biomes, or a biome that is associated with fresh water, would consist of the plants, the animals, and really all the kingdoms that would be associated in that system. So your your Archaea kingdom, your Protista kingdom, your bacteria kingdom, your fungi kingdom, your Animalia kingdom, and your Plantae kingdom, all of them play a very important role in forest management. When it comes to managing a forest, you really need to look at it holistically. From a point of view is these forests need freshwater systems. Freshwater systems are going to directly affect not just the Plantae kingdom, but also the Animalia, fungi, bacteria, etc. And so that's why when we talk about a freshwater biome, we need to talk about all of those things that live in or near water. So often confused or often misinterpreted is the term fresh water. What does it mean to be fresh water? Okay. Well, often people would say, well, it's clean, okay, or it's clear, but in actuality, that has nothing to do with it. Okay, fresh water is still stagnant, muddy, polluted. Could be hot, cold, loaded with dissolved materials. It doesn't really matter. The fresh comes from the concentration of dissolved salts during a given period of time. I want you to make sure that you understand fresh water is not always fresh water. Okay. For example, in the spring, okay, when rainfall, snowmelt comes, a lot of streams and ponds and lakes and whatnot are considered freshwater systems because the concentration of dissolved salts are low. As that system moves into the summer and evaporation takes place and no new freshwater sources are coming in or very little, and evaporation is taking place, the amount of dissolved salts increases, okay, in those environments. And you might go from a system that's considered fresh in the spring to in the fall having 20 times the dissolved salt levels as marine systems. Okay, so far more saline systems. Okay, where in the spring it's considered 100% fresh water, or would definitely be considered fresh water, and in the fall it's considered a saline system or salt water. Okay, you have to keep those things in mind, especially in desert regions where you might be managing a forest that occurs in a desert region, where in the spring it has a great freshwater source, but by the time you get to the fall, that freshwater source is no longer a viable source of water for that forest or for those organisms in that forest. Okay, when we look worldwide, freshwater biomes consist of about 2.5 to 2.75% of all the water on the planet is considered fresh. Okay, that is broken up by 2% glacier. Okay, so most of that is not available. So you're looking at roughly 1% or close to 1% of the available water on the planet would be considered fresh water. A lot of that's groundwater, with leftover very little water for terrestrial environments. Okay, so 0.01% is wrapped into lakes and rivers. The 0.1% is basically what's feeding all your forests across the planet. Okay? So it's important for us to consider alterations like pollution that might affect that 0.01%, because that's going to have a direct impact on our forest management capabilities. Okay, so let's dive a little deeper into freshwater habitats. You have two main types. You have lotic habitats. Lotic habitats, you can think of them as load bearing or load carrying habitats. So these are habitats that move. Okay, they move freely, the water moves freely. This would be streams, creeks, rivers, okay, whatever you want to call them. Okay, but they're moving bodies of water, freely moving bodies of water. Okay? Now, we have to talk about where is the energy coming from. Okay? This is the main thing that kind of differentiates between a lotic habitat and a lentic habitat. The lotic habitat, its energy is almost all coming from allochthonous energy. Okay, allochthonous energy means it's coming from outside the system. Autochthonous energy means it comes from inside the system. Okay, so lotic habitats are very limited, for the most part, in autochthonous energy, okay, or energy that's coming from within. Okay, they have a heavy amount of energy that's coming from outside the system, or allochthonous energy. Okay, we'll come back to this and I'll show you some examples of this in just a second. So the second habitat is a lentic habitat. This is not free-flowing water. Okay, so it has little movement. Yes, it might cycle. Yes, it might be fed by a lotic habitat, and you might get some wave action, things like that. But the water stands still for the most part. And this would be swamps, ponds, wetlands, lakes. They have lots of different names. Okay. Now, depending on the system, okay, will depend on how much ectoctomous versus how much allochthonous energy is in that system. Okay. The reason lentic habitats are interesting is because a lot of this has to do with depth, has to do with what surrounds the lentic habitat. Do you have heavy loads of vegetation? What's feeding the lentic habitat? Do you have a lotic habitat feeding the lentic habitat? So it's getting a lot more allochthonous energy coming into the system? Or is that a freestanding habitat, freestanding lentic habitat, where majority of the energy has to be built from within? Okay, so again, what am I talking about when I'm talking about allochthonous versus autochthonous? Okay, allochthonous energy are things like leaves, okay, that are flowing into the system, branches, carcasses of organisms, okay, these kind of things. The energy is coming from outside the system, it gets into the system, okay, and then the organisms within that system can use that energy. Yes, you can see here some autochthonous energy. You can see these mosses, okay, you can see the algae and things like that that might be occurring in some of these regions where the water is slowed down, etc. That's autochthonous energy, okay, energy that's made from within the system. Okay? A wetland or a pond or a lake, okay, if it's shallow enough where the sun rays can penetrate it and it has vegetation, plants, okay, that's autochthonous energy. That's energy built from within the system, okay, not energy, allochthonous energy coming from outside the system. Okay, so those are the two main differences between the two systems, besides water flow and non-flow. So that brings us to the role that vegetation plays, or for a better example, forests play in these systems, especially in those allochthonous systems. Okay? An allochthonous system, streams, rivers, okay? Most of their energy is coming from outside the system. It's coming from the landscape. Okay, it's coming from the vegetation on the outside that falls that falls into the system, okay, when it falls into the system, okay, and then things can break down those trees. They break down those leaves. They break down those pine needles. They break down that vegetation. And they can use that energy to feed the organisms within the system. Okay? That's why trees and vegetation in rivers and streams is so important, because that's really the only way they're going to get their energy. Okay? Well, in the 1950s, all the way until about the 1990s, and even before the 1950s, but because of the 1950s, we really ramped up our logging operations, and we had better technology to start cutting more and processing more material in right after World War II, right after World War II, we kind of really started ramping up our processing of trees. And so the 1950s really hit a point where we decided, hey, one way to get logs quickly to a log mill is to cut them close to a stream and drop them in, or close to a river, drop them in and float them down the rivers, okay, to a logging operation. And we used to do this a lot. So the stream sides and river sides were barren of trees, because they're dropped into the river. Obviously, this one's not going to flow a log down it, but a big river, we'd float the logs down, okay, that came alongside of the tree, alongside of that river. We'd float them down. Okay? Well, what we were doing, and we didn't realize it, is we were taking the nutrients for that loading system, and we were removing it. We were taking the energy and we were removing it. Apart from that, we also started changing the system. Okay? If you have no more vegetation in the system, the flow of the system is straight. Okay? It's a straight shot, and it just starts cutting away banks, and it takes the easiest route wherever it's going. Okay? But if you have vegetation that lands in the stream or the river, okay, it will start to build up things like gravel bars, okay, pools, a central bar that occurs after that vegetation log. And over a long period of time, you get islands that occur. Okay, you get back channels that occur. You create these new ecosystems. Islands are amazing places for wildlife, like birds, to lay their eggs and build nests on islands, because predators typically can't get to those islands. These gravel bars are excellent regions for fish to build their nests or spawn. Okay? These pools are excellent regions for fish to get out of the current and feed. Okay? And so there's just so much of the activity that when you have forest material falling into the streams and lodging in the streams, that it creates these niches in environment that you don't see in a free-flowing straight line stream or a straight line river. And therefore, you can really change the environment. So when we started removing trees from the water, from the system, we started cutting all the trees down along the edges of the rivers, okay, and floating them down and utilizing that wood. You no longer had these systems, these gravel bar systems, these islands forming, etc. So what does it do? Well, here's some data. Okay? So this data is fairly old, but it was an old practice. We've changed our ways. Okay, but nonetheless, it shows you a good example of what happens if you log alongside of streams. So This is a river, the Kangzuvara, and you can see that when we look at what happened to the river after logging, you can see that the flow rate, the runoff, is much higher after logging than before logging. Okay? You can see that in January to June. You can also see that July to December. Okay? The amount of flow, the amount of runoff is far higher after logging than it is before logging. Okay? What that tells us is not only were the trees holding back some of the water for the landscape, for the terrestrial environment, if the runoff is greater after, it means that you're probably carrying more silt, more nutrients, more water, obviously, down the stream. Okay, so you're basically blowing out the stream, okay, and you're making it more streamlined. That becomes problematic. Okay? The other main thing that we see, and a huge problem when it comes to fisheries science, is when you remove, okay, and this stream, the material was removed in 1956 from this stream. You can see right after removal in 1956, temperatures around the stream, okay, the temperature in the stream, the average temperature in the stream started jumping. The maximums jumped, but the averages jumped also, and they started jumping up. Well, if you get into that 25 degrees Celsius water temperature, these are maximum temperatures, okay, it's reaching 25, multiple years it's reaching 25. Well, some fish can't tolerate temperatures that high. So if the water is getting to a temperature that high, even though the average just trickling up. I mean, the average is going from about 12 degrees, maybe up to 14 degrees. But it's these thermal maximums, these maximums that are going on because now you have no trees along the edge of your river, so you don't have any shade. So you have no shade, so you have extreme sun, temperatures warming the water, okay, and you can get these high maximums. Maybe the average is not ticking up too much over, the years, okay, from the 1950s into 2000. Okay, maybe it increased by 2 degrees. The river itself increased by 2 degrees on average. Okay, it's the maximums that get scary though. If the fish are already sitting at 21 degrees is where is their maximum, but now you're jumping all the way to 25, that can be problematic. So let's look at what this means for things like coho salmon, steelhead salmon, etc. So here's the temperature graph, okay? And this is associated with growth rate. Okay? So if you look at temperatures, here's 20 degrees Celsius, there's 25 degrees Celsius, so this is probably 22.5 degrees Celsius. Once you get to 25 degrees Celsius, you pretty much have 100% of a decrease in growth rate. Okay? So that's what this is showing. Okay? The optimal growth rate for these fish is 19 degrees. The optimal growth rate for steelhead is right around that 19 degree mark. They can tolerate things up to 40%, even 60%. But when you're getting up there into the 25 degrees Celsius, okay, these fish are not growing. They're maintaining, but they're not growing. So your fish are getting smaller and they're experiencing thermal stress. So what they do when the average temperature, that maximum temperature is getting to 25, instead of going out and feeding, they're staying in the shady parts of the river for a much longer period. Maybe in the deepest pools of the river, they're staying there for a much longer period. Okay, and they're waiting out the summer. So that's where the decrease in that growth rate is coming from. Okay? They're not feeding as often. So they have to basically utilize their fat reserves for a much longer period of time. Okay? There's lots of other cases in which we have issues from, you know, poor logging management on streams and rivers. Okay, but from a standpoint of lintic and lotic systems, okay, it really depends on where's the source of energy. Is it a Loch Ness energy? Is it coming from outside? If it's coming from outside and you've removed all the vegetation, well, you've just limited your stream's energy output. Okay? If it's a system where autochthonous, where it can be built within, then cutting the edges of the stream might allow more light, and you might get a lot more energy coming in, maybe too much. And you can get what we call algae blooms, okay? And you can get a huge amount of energy coming in, and it can decimate the oxygen levels and kill off the system. Okay, so that's the start of the wildlife and forest kind of lecture. The next component that I'm going to talk about is the role that this plays in dictating the higher order organisms. Okay, so the mammals and the birds, even amphibians and reptiles, okay, things that might not spend their entire life in aquatic environments. Okay, next time.